Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So for this week we will learn about layer 4, which is transport layer, and we also add also quality of service, which is related to layer 4. So basically the transport layer is a crucial component of the OSI, so Open System Interconnection model. So it's responsible for the end-to-end delivery of data between hosts on a network. So it sits above the network layer uh, and below the session layer. So providing a reliable and efficient communication channel. So quality of service QoS refers to a set of techniques and mechanisms that aim to ensure the delivery of data with specific performance characteristics such as reliability, timeliness, and efficiency. So QoS plays a vital role in maintaining network performance and meeting the requirements of different applications and users. So in this presentation, we will explore the transport layer and delve into various aspects of quality of service and understanding its importance in achieving reliable and efficient communication. So now let's delve into some of the common transport layer protocols that are widely used in the network communication. So when you join the network field as a carrier, so you can see a lot of TCP and UDP protocol involved in that. So so the two prominent protocols that we will focus on are TCP, which is transmission control protocol, and UDP, which is a user datagram protocol. So TCP, which stands for transmission control protocol, is a connection oriented protocol. It establish a reliable, okay, the key point is reliable and ordered delivery of data between two communicating hosts. So TCP ensures that the data arrives at its destination without errors or in the correct sequence. So to accomplish this, TCP utilizes various mechanisms such as error detection, retransmission, flow control, and congestion control. So the connection-oriented nature of TCP means that a logical connection is established between the sender and the receiver before the data transmission can occur. So this connection is created through a process called the three-way handshake, where the two hosts exchange control messages to synchronize their communication. Once the connection is established, TCP provides a reliable and robust channel for the transfer of data. So on the other hand, UDP, which stands for User Datagram Protocol, is a connectionless protocol. So unlike TCP, UDP does not establish a formal connection before transmitting data. So instead, it operates on a best effort basis, providing a fast and lightweight delivery mechanism. UDP is commonly used in scenario where speed and low overhead are prioritized over reliability. So UDP is often preferred for real-time applications such as audio and video streaming, so online gaming and DNS domain name system lookups. Since UDP does not have the mechanism for error recovery and retransmission present in TCP, it offers reduced latency but does not guarantee the delivery or ordering of data packets. So in summary, TCP and UDP are two contrasting transport layer protocols, and TCP ensures reliable and ordered delivery, making it suitable for applications where data integrity is crucial, And UDP, on the other hand, prioritize speed and efficiency, making it suitable for real-time application where low latency is essential and occasional packet loss is tolerable. So the choice between TCP and UDP depends on the specific requirements of the applications and the desired trade-off between reliability and performance. So for this slide, let's explore the key features of the transmission control protocol, which is TCP, which ensure reliable communication between hosts. So TCP incorporates several mechanisms that contribute to its reliability. So the first one is error detection. So TCP employs a checksum mechanism to detect errors in transmitted data, and a checksum is calculated for each TCP segment, and the receiving end verifies the integrity of the data by comparing the calculated checksum with the received checksum. So the second one is retransmission. So in the event that a TCP segment is lost or corrupted during transmission, TCP initiates retransmission. So the sender, upon receiving acknowledgement of missing or corrupted segments, retransmits the data, ensuring that it reach the destination reliably. So the third one is flow control. TCP utilize flow control mechanism to prevent the receiver from being overwhelmed by an excessive influx of data through the use of Windows-based flow control. So TCP regulates the rate at which data is sent, ensuring that the receiver can handle the incoming data comfortably. And the fourth one is congestion control. TCP also implement congestion control mechanisms to manage network congestion effectively. So TCP use various algorithms such as TCP Reno and TCP Vegas to detect and respond to network congestion. So these algorithms adjust the sending rate of TCP traffic to elevate congestion and maintain network stability. In addition to these features, TCP establish a connection to a process known as three-way handshake. So there are three-way handshake. The first one is synchronized (SYN) segment. So the initiating host send a synchronized segment to the destination, indicating its intention to establish a connection. And then secondly, synchronized acknowledgement segment. The destination host receive the synchronized segment, acknowledge it, and responds with a synchronized sync ACK segment. So this segment confirms the receipt of the SYN segment and signifies the readiness to establish a connection. Third, acknowledgement segment. The initiating host acknowledge the sync acknowledge segment, and the connection is established. So from this point forward, data transmission can occur bidirectionally. Lastly, the TCP segments have a specific structures that enables effective communication. TCP segments consist of header and a data section. And the header includes fields such as source and destination port numbers, sequence and acknowledgement numbers, control flags, and window size. So the data section carries the actual payload or application data. And this TCP features, along with the three-way handshake and segment structures, contribute to the reliability and efficiency of TCP communication. Okay, for this slides, let's now shift our focus to the user datagram protocol UDP. So, and explore its distinctive features. UDP offers several advantages. First, low overhead, which is UDP has a minimal header overhead compared to TCP. This lower overhead makes UDP a lightweight protocol suitable for applications where efficiency is crucial. Second, minimal delay. So UDP is a design for low latency communication. It has less built-in processing and error recovery mechanisms compared to TCP, allowing for faster transmission and reduced delay. Simplicity. So UDP is simpler in design compared to TCP. It has fewer features and less complexity, making it easier to implement and manage. So, due to these advantages, UDP is commonly used in specific use cases, including real-time streaming. So, UDP is ideal for real-time streaming applications such as video streaming, live broadcasting, and audio streaming. This application prioritize a continuous flow of data and can tolerate occasional packet loss. Video conferencing. So UDP is also commonly used in video conferencing systems where real-time communication and low latency are essential for smooth and interactive conversations. And then DNS, domain name system, is the protocol of choice for DNS queries where quick response times are crucial. So DNS queries are typically short and require a fast round-trip communication. Gaming. So many online gaming applications utilize UDP due to its low latency nature, allowing for real-time interaction between players and reducing the impact of delays on the gaming experience. However, it is important to note that UDP lacks the reliability and error recovery mechanism found in TCP. Since UDP is connectionless, there is no guarantee of delivery or ordered transmission of data, and UDP does not perform automatic retransmission of lost or corrupted packets. It is up to the application layer to handle error detection, recovery, and ordering if required. So, in summary, UDP's advantages lies in its low overhead, minimal delay, and simplicity. It is well suited for use cases where real-time streaming, low latency communication, and reduced overhead are prioritized. However, due to its lack of reliability mechanisms, it is crucial for application utilizing UDP to handle error recovery and ordering as needed at the application layer. So that's for TCP. For this forward, we jump into quality of service overview. So let's move on to discussing quality of service (QoS) and its significance in network communication. So very important QoS. So QoS can be defined as a set of techniques and mechanisms that aim to manage and prioritize network resources to meet specific performance requirements. So it involves implementing strategies to ensure that different applications and users receive the appropriate level of service they require. So the importance of QoS lies in ability to provide different levels of service to applications and users based on their specific needs. So not all packets are equal, and uh, different applications have varying requirements in terms of bandwidth, latency, jitter, and packet loss. So QoS parameter refer to specific performance characteristics that are considered when implementing QoS mechanisms. So these parameters include first bandwidth. So bandwidth refers to capacity of a network to transmit data within a given time frame. QoS mechanisms can allocate prioritized bandwidth to ensure that the critical applications or high priority traffic receive sufficient bandwidth for their needs. Second, latency. Latency is the time delay between the transmission and reception of packets. Low latency is crucial for applications that require real-time communication, such as voice, video conferencing. QoS mechanisms can manage and minimize latency to maintain smooth and timely data delivery. So third, jitter. So jitter refers to the variation in the latency of data packets. So in real-time applications such as streaming or voice over IP that we always use in call center usually, consistent and low jitter is essential to avoid disruptions and ensure a seamless user experience. So QoS mechanism can help mitigate jitter by managing network congestion and prioritizing real-time traffic. Fourth, packet loss. So packet loss occurs when one or more data packets fail to reach their destination. So high packet loss can significantly impact the quality of communication and the overall user experience. The QoS mechanisms can minimize packet loss through error recovery mechanisms, redundancy, and efficient network management. So by considering these QoS parameters and implementing appropriate techniques, network administrator can prioritize critical traffic allocated resource effectively and ensure that the network meets the performance requirement of different application and users. So in summary, QoS encompass techniques and mechanisms that manage and prioritize network resources to provide different levels of service. So understanding and implementing QoS is essential to optimize network performance and ensure reliable communication and meet the specific needs of diverse application and users. So now let's explore the various QoS mechanisms that are used to manage and optimize network resources. First, traffic prioritization. So traffic prioritization involves assigning priorities to different types of network traffic based on their importance or requirements. So this allows critical traffic such as real-time voice or video communication to be given higher priority to ensure timely delivery and minimize delays. So QoS mechanism use techniques like differentiated service code point (DSCP) or class of service (COS) to mark and prioritize packets accordingly. Second, traffic shaping. Also, traffic shaping is a technique used to control the rate of data flow within a network. It ensures that network resources are used efficiently and prevents congestion. So by regulating the flow of traffic, QoS mechanism can manage and prioritize certain types of traffic over others. So traffic shaping can be applied through methods like token bucket or leaky bucket algorithms, where the rate of data transmission is controlled to match the available network capacity. Third, congestion control. Control mechanisms are employed to manage network congestion, which occurs when the demand for the network resources exceeds its capacity. Congestion can lead to increased latency, packet loss, and degraded performance. And QoS mechanisms such as TCP congestion control algorithm like TCP Reno or TCP Vegas detect and respond to congestion by adjusting the transmission rate and reducing the load on the network. So fourth, resource renovation. So resource reservation. Resource reservation involve allocating specific network resources such as bandwidth or buffer space in advance to meet the requirement of certain application or services. So this ensures that the necessary resources are reserved and available when needed. So guaranteeing the quality of service for those applications. So resource reservation mechanism like RSVP, resource reservation protocol, enable applications to request and reserve network resources to ensure desired level of performance. So these QoS mechanisms work together to optimize network performance, prioritize critical traffic, manage congestion, and ensure that the network meets the specific requirements of different applications and users. So by implementing these mechanisms, network administrators can maintain a high quality of service, minimize delays, and allocate resource efficiently. So let's explore the concept of congestion control, which is crucial for managing network performance when demand for network resources exceeds its capacity. First, the definition of congestion. Congestion occurs when the amount of traffic attempting to use a network exceeds its available capacity. So it leads to increased delays, packet loss, and degraded performance. So congestion can arise due to various factors such as high network utilization, limited bandwidth, or network bottlenecks. Second, congestion control mechanisms. So congestion control mechanisms aims to detect and manage congestion to maintain optimal network performance. So two primary approaches to congestion control are congestion avoidance and congestion control algorithm. So congestion avoidance mechanism are designed to prevent congestion from occurring or escalating. So this mechanism use feedback techniques to monitor network conditions and adjust the transmission rate accordingly. So by dynamically controlling the rate of data transmission, congestion avoidance techniques help regulate the flow of traffic and prevent network overload. And congestion control algorithms are employed when congestion is detected or anticipated. So these algorithms aim to alleviate congestion and restore network stability. One well-known example is congestion control algorithms implemented in the transmission control protocol. So the TCP use various congestion control algorithms such as TCP Reno and TCP Vegas to adaptively adjust the transmission rate based on the observed network conditions, congestion signals, and packet loss. So congestion control algorithms monitor network congestion indicators such as round trip time, packet loss rate, and available bandwidth. So they dynamically adjust the congestion window size, retransmission behavior, and retransmission rate to mitigate congestion and maintain efficient data delivery. So by implementing congestion control mechanism, networks can effectively manage congestion, reduce packet loss, and maintain reasonable delay, and ensure fair resource allocation among users. So in summary, congestion control aims to prevent or alleviate congestion by adjusting transmission rates and regulating network traffic. This mechanism plays a crucial role in maintaining network performance and ensuring high quality user experience. Examples of congestion control algorithm includes those implemented in TCP such as TCP Reno and TCP Vegas. So let's explore the next concept of bandwidth, which is bandwidth allocation, which is an essential aspect of quality of service. Bandwidth allocation techniques determine how network resources are distributed among different applications or users. So basically, in bandwidth allocation techniques, there are two main approaches to bandwidth allocation: static allocation and also dynamic allocation. So for the static allocation involve the fixed allocation of bandwidth based on predefined rules or priorities. So network administrators allocated specific amount of bandwidth to different applications or users in advance. So this fixed allocation ensures that certain applications or service receive a guaranteed portion of the available bandwidth at all times. And static allocation is suitable for scenario where bandwidth requirements are well defined and relatively stable. For dynamic allocation, also known as adaptive allocation, involve the allocation of bandwidth based on network conditions and demand. With dynamic allocation, bandwidth is assigned in real time, responding to the changing requirements of applications or users. So these techniques allow for flexibility and efficient utilization of network resources. And dynamic allocation is particularly useful in situations where bandwidth demands vary over time, or where there is need to prioritize certain types of traffic dynamically. So the choice between static and dynamic allocation depends on the specific requirements of the network and the application being supported. Static allocation provides predictability and ensures a dedicated portion of bandwidth for critical applications. On the other hand, the dynamic allocation enables efficient utilization of available resources by adapting to changing network conditions, demand. So QoS, a mechanism for bandwidth allocation, may employ techniques such as traffic prioritization, quality of service parameters, and policies defined by network administrators to determine the appropriate allocation strategy. So in summary, bandwidth allocation techniques plays a crucial role in QoS. Static allocation offers fixed bandwidth allocation based on predefined rules, while dynamic allocation adapts the bandwidth allocation based on real-time network condition and demand. So the choice of allocation techniques depend on the specific needs and characteristic of the network and the application it support. Okay, now let's delve into latency and jitter, two important factors in network communication, and explore QoS techniques to manage them effectively. So first, latency. So latency refers to the time it takes for packet to travel from the source to the destination. It includes the time spent in transit and the processing time at various network devices. So latency is typically measured in milliseconds. Low latency is essential for real-time applications like video conferencing, online gaming, voice over IP, where delays can impact the user experience. Second, jitter. Jitter refers to the variation in latency experienced by packets in a network. So it occurs due to differing transmission delays encountered by packets as they traverse the network. So jitter can cause disruption in real-time applications as it leads to inconsistent timing and can result in packet loss or out of order delivery. So managing jitter is crucial to maintaining the quality and continuity of real-time communications. So QoS technique to manage latency and jitter. First is buffering. So buffering is techniques that involve temporarily storing packets in a buffer to mitigate the effects of latency and jitter. So by introducing a buffer, packets can be received and stored until they can be transmitted smoothly. So buffering helps smooth out variations in latency and reduce the impact of jitter by allowing packets to be delivered at more consistent rate. Second, traffic engineering. So traffic engineering involves the strategic management and control of network traffic to optimize performance and reduce latency. It includes techniques such as route optimization, load balancing, and traffic prioritization to ensure efficient and effective use of network resources. So queuing algorithm play a significant role in managing latency and jitter by determining the order in which packets are processed and transmitted. So QoS mechanism utilize different queuing algorithm such as priority queuing, weighted fair queuing, or class-based queuing (CBQ) to give priority to certain types of traffic or ensure fairness among different flows. So by implementing these QoS techniques, network administrators can mitigate latency and manage jitter effectively, ensuring smoother and more reliable communication. especially for real-time applications. So, in summary, latency and jitter are important factors in network communication. Latency refers to the time it takes for packet to travel from source to destination, while jitter represents the variation in latency. So QoS techniques such as buffering, traffic engineering, and queuing algorithm are employed to manage latency and jitter, providing a better quality of service for real-time application. So let's now explore the concept of packet loss and the techniques used in quality of service QoS to mitigate its impact on network communication. So packet loss refers to the failure of one or more packets to reach their destination. It can occur due to various reasons, including network congestion, transmission error, or limitation in network devices. So packet loss can have a detrimental effect on application performance, resulting in reduced data integrity, increased latency, and degraded user experience. Effects of packet loss on application performance. Packet loss can lead to several negative consequences for network applications. So it can cause data corruption or missing data, resulting in distorted or incomplete information. So in real-time applications such as video streaming or voice communication, packet loss can cause interruptions, jitter, or noticeable gaps in the media stream. So for data-intensive applications such as file transfers or database transaction, packet loss can lead to retransmissions and delays and reduce throughput. So QoS techniques to mitigate packet loss. First, forward error correction (FEC). So FEC is technique that adds redundancy to transmit packets, so it enables the receiver to detect and correct errors without requiring transmission. So by including error correction information in each packet, FEC can recover lost or corrupted data packets at the receiving end, and reducing the needs for retransmission and minimizing the impact of the packet loss. Retransmission. Retransmission is widely used technique to mitigate packet loss. When packet loss is detected, the receiver requires the sender to retransmit the lost packets, and the sender detects the missing packets and resend them, ensuring their successful delivery. So retransmission mechanisms such as automatic automatic repeat requests (ARQ) are implemented in various protocols including TCP. So redundancy involves duplicating or replicating data packets to mitigate packet loss. So by sending multiple copies of the same packet through different network paths, the likelihood of all copies being lost simultaneously decrease, and redundancy can be implemented at various levels such as the application layer or through techniques like multicast or multiple transmission. So by employing these QoS techniques, network administrators can minimize the impact of packet loss, enhance data integrity, and improve the overall performance and reliability of network communication. So in summary, packet loss can have detrimental effects on application performance. QoS techniques, including forward error correction, retransmission, and redundancy, are employed to mitigate packet loss and improve the quality of service. So these techniques help ensure data integrity, reduce interruptions, and maintain a smooth and reliable communication experience. Next, let's explore the concept of the differentiated service. DiffServe, a quality of service model that provides different levels of service based on traffic classification. So this serve is a QoS model that aims to differentiate and prioritize network traffic based on its characteristics and requirements. So it provides a framework for managing network resources efficiently and delivering a different level service to various types of traffic. So this serve architecture involves several key components. First, classification. Traffic classification is the process of identifying and categorizing network traffic based on certain criteria, such as packet headers, protocol type, source or destination addresses, or application specific requirements, and then different classes or groups of traffic are defined based on their importance or quality requirements. Marking. So once traffic is classified, it is marked with a specific code or value in the packet header. These markings indicate the priority of service level assigned to each packet. So commonly used marking techniques include differentiated service code point or type of service field in IP header. Queuing. Queuing refers to process of managing the order in which packets are processed and transmitted. Different queues are used to hold packets belonging to different traffic classes or priorities. So queuing mechanisms such as priority queuing or weighted fair queuing ensure that high priority traffic receive preferential treatment and is transmitted ahead of lower priority traffic. Traffic conditioning. Traffic conditioning involves shaping or policing the traffic to enforce predefined policies or limits. It helps in controlling the flow of traffic and ensuring that it conforms to the service assigned service level agreements or quality requirements. So selanjutnya kalau dalam dalam IT service ni, dia mesti ada kontrak tentang service level agreement, berapa apa ni certain level yang dia orang agree yang perlu deliver. So benefits of this serve offer several benefits in managing network resources efficiently, and then scalability. So this serve provide a scalable approach to QoS as it can handle large scale networks with a wide variety of traffic types and requirements. So by categorizing traffic into different classes, this serve enables efficient resource allocation and management. Then next is flexibility. So this serve offer flexibility in defining and customizing service level based on specific needs and requirements. It allows network administrator to prioritize critical traffic, allocate resource accordingly, and adjust QoS parameters as needed. So quality differentiation. This serve allow for different levels of service based on traffic classification. This enable applications with higher quality requirements such as real-time communication or critical data transfers to receive preferential treatment and guaranteed level of service. So and then a resource optimization. By optimizing by priority sorry by prioritizing and managing traffic based on its importance or requirements. This serve optimize the utilization of network resources. So it ensure that critical traffic receive appropriate resources and prevents network congestion or degradation due to the overload of lower priority traffic. So in summary, this serve is a QoS model that provide different level of service based on traffic classification. Its architecture includes traffic classification, marking, queuing, traffic conditioning, and this serve offers scalability, flexibility, quality differentiation, and resource optimization, making it an efficient approach to manage network resources and delivering a level of services. So let's move to let's discuss the challenges associated with implementing QoS, quality of service, and the consideration that need to be addressed for successful implementation. So first, challenges in implementing QoS. First, network complexity. Implementing QoS in complex networks can be challenging due to the presence of various devices, protocols, and traffic types. So coordinating QoS mechanisms across different network elements and ensuring consistent behavior can be complex. Next is interoperability. So ensuring interoperability among different network devices and software components is crucial for QoS implementation. Compatibility issues may arise when deploying QoS mechanisms from different vendors or integrating them into existing network infrastructure. Scalability. Scaling QoS mechanisms to large networks can be significant challenges. Can be a significant challenge. As network grows in size and complexity, the management and control of QoS become more challenging, and ensuring consistent QoS across a vast network uh, while efficiently utilizing resources requires careful planning and coordination. Second, balancing QoS requirements with performance and cost consideration. So, implementing QoS involve finding the right balance between meeting QoS requirements and considering network performance and cost factors. So, allocating resources and implementing QoS mechanisms to meet specific service level agreements SLA must be done without compromising overall network performance or exceeding cost constraints. So importance of uh, proper configuration and ongoing monitoring of QoS mechanisms are critical for successful implementation. So configuration should align with the network requirements, traffic patterns, and QoS policies. So regular monitoring and analysis of QoS parameters and performance metrics identify issues, optimize resource allocation, and ensure that desired QoS levels are being achieved. So successfully implementing QoS it requires a thorough understanding of the network environment, and careful planning and coordination among different network elements, and it is essential to address the challenges of network complexity, interoperability, and scalability. So striking a balance between QoS requirements, network performance, and cost consideration is vital, while proper communication and ongoing monitoring are necessary to maintain desired QoS levels. So in summary, implementing QoS comes with challenges related to network complexity. So interoperability and scalability, and then balancing QoS requirements with network performance and cost consideration is crucial. Proper configuration and monitoring of QoS mechanisms play a pivotal role in ensuring successful implementation and maintaining the desired quality of service levels. So let's go depth into one of case study. So QoS in voice over IP. So in this case study, let's explore the importance of quality of service in voice over IP, especially used in customers call center. Voice over IP applications and the specific QoS techniques employed to ensure clear and uninterrupted voice communications. So importance of QoS in voice over IP. QoS plays a crucial role in voice over IP applications due to the real-time nature of voice communication. So voice over IP transmit voice data packets over IP networks, and any delay, packet loss, or jitter can severely impact call quality. So QoS ensure that voice over IP traffic receive the necessary priority, bandwidth, and efficient management to maintain high quality voice communication. So QoS techniques specific to voice IP, prioritization of voice traffic. So voice voice IP traffic should be given high priority to minimize delay and ensure timely delivery. So traffic classification mechanisms identify voice packets and assign them higher priority over other types of traffic, and this ensure that voice packets are transmitted promptly and experience minimal delay. Next is bandwidth allocation. So sufficient bandwidth allocation is critical for voice over IP application to maintain high quality. So QoS mechanism allocate an appropriate amount of bandwidth specifically for voice IP traffic, ensuring that voice packets are transmitted without congestion or delay. So this helps prevent degradation in voice quality due to insufficient bandwidth. So jitter management. Jitter, the variation in latency can disrupt voice communication in voice IP application. So QoS mechanism implement jitter management techniques such as buffering and traffic shaping to minimize the impact of jitter. So buffering temporarily stores voice packets, allowing for smoother and more consistent delivery, while traffic shaping regulates the flow of packets to control jitter. So by employing these QoS techniques specific to voice over IP, network administrators can ensure that voice communication remain clear, reliable, and uninterrupted. So priority voice traffic, allocating sufficient bandwidth, and effectively managing jitter contribute to optimal voice IP performance. So in summary, QoS plays a vital role in voice over IP application to maintain high quality voice communication. Specific QoS, sorry. Okay. Jitter management. Jitter management. Jitter, the variation in latency can disrupt voice communication in voice IP application. So, QoS mechanism implement jitter management techniques such as buffering and traffic shaping to minimize the impact of jitter. So, buffering temporarily stores voice packets, allowing for smoother and more consistent delivery, while traffic shaping regulates the flow of packets to control jitter. So by employing these QoS techniques specific to voice IP, network administrators can ensure that voice communication remains clear, reliable, uninterrupted, and prioritizing voice traffic, allocating sufficient bandwidth, and effectively managing jitter contribute to optimal voice API performance. So case study number 2, which is QoS and video streaming. Uh, let's in this case study, let's explore the quality of service consideration specific to video streaming applications and the techniques employed to ensure smooth and uninterrupted video playback experience. So QoS consideration for video streaming bandwidth, allocation bandwidth is critical in video streaming to ensure continuous and high quality viewing experience. So QoS mechanism allocate sufficient bandwidth specifically for video traffic, uh, prioritizing it over other types of traffic. This allocation helps prevent buffering and ensures smooth playback by delivering video packets without congestion or delays. So latency and jitter management. So latency and jitter management are essential for video streaming to minimize buffering and improve the user experience. So QoS techniques are employed to manage latency by reducing the delay between data transmission and reception jitter. Jitter management techniques such as buffering and traffic shaping help mitigate variations in latency and deliver video packets consistently, reducing interruption and ensuring smooth playback. Packet loss mitigation. Packet loss can severely impact video quality and lead to interruptions or visual artifacts in video streaming. So QoS mechanisms implement packet loss mitigation techniques such as forward error correction, retransmission, and redundancy to recover lost or corrupted video packets. So these techniques help maintain video quality, prevent interruptions, and enhance overall viewing experience. So by considering these QoS aspects and employing the relevant techniques, video streaming application can deliver a smooth, uninterrupted viewing experience to users. So effective bandwidth allocation, latency and jitter management, packet loss mitigation contribute to optimal video playback quality and user satisfaction. So for conclusion with the this session is transport layer is in fostering reliable efficient communication. So when it comes to data transmission, this layer stands as the bridge that facilitate the movement of data packets between source and destination across the network. So it does so by effectively managing the flow of information, ensuring its error-free transfer, error-free transmission, and verifying the successful delivery of packets, whether it's about establishing connection, overseeing error correction, or orchestrating flow control. The transport layer has its parts to play. So this layer without doubt forms the cornerstone of the provision of reliable connection-oriented communication service. So moving on, quality of service, colloquially known as QoS, marks as importance in the sphere of managing network resources and guaranteeing different levels of service. So QoS techniques have evolved into essential tools for the fine-tuning and optimization of networks, thereby ensuring the ability to cater to a plethora of service with diverse performance requirements. So QoS techniques allow network administrators to determine the precedence of traffic flow and thus ensuring priority treatment for latency sensitive and mission critical data. So this capability is particularly useful in today's highly diversified network environments where myriads of applications with varying network demands coexist. So with QoS, we can ensure fair allocation of network resources, maintain the highest possible level of performance, and effectively manage congestion when it arises. Therefore, having a comprehensive understanding and efficient implementing QoS mechanism is no longer a choice but a necessity. It becomes the backbone for delivering a seamless user experience and optimizing network performance. To conclude, in this era of rapidly advancing technology and increasing reliance on network communication, the transport layer and QoS techniques are undeniably essential. Their roles in maintaining the reliable of data transmission and managing network resources and optimizing performance are instrumental in driving the digital world. So by understanding and implementing these crucial elements, we can continue to provide, maintain, and improve a seamless digital experience for all users in all situations. Okay, thank you everyone. That's all for this session.